So we've already shown that the difference between two even integers is going to be another even integer. Does that same kind of intuition hold for odd integers? Is the difference between any two odd integers going to be odd? Well, because we're looking at any two integers, this is a for all proof. So let's write down what we're actually asking. For all a, b that are integers is, if a and b are odd, is a minus b odd, right? And what should we always do? Think of some examples. Think of the easiest things you can think of. Well, the first thing I would think of is, well, odd numbers would be like 1, 3, 5, and then -1, -3, -5, right? Well, let's ask ourselves, okay, let's do 3 minus 3. That's two odd numbers. We're doing any, they could be the same. So 3 minus 3, that's 0. 0 is not odd. 0 is actually an even number. So we've already shown that this statement is false. It's not for all odd integers. We've already shown that for the same odd integer, the difference is always going to be even. Well, before we start writing that, let's just check one more time. Let's do 5 minus 3. Well, that's going to be 2, and 2, of course, is even. Okay, so we have more than enough evidence to show that this statement is false. So how do we prove this is false? Well, we start by first writing out the negation of our statement and then proving the negation of the statement is true. So let's quickly do that. Okay, so the negation of a for all is always going to be a there exists. So our negation is going to end up being there do exist integers a and b where a and b are both odd, but a minus b is not odd. I could have written even, but let's play it safe and just say not odd, because maybe we find that the difference is also not even either, right? So how do we prove our red statement here? Well, we say, for example, let a comma b be integers. You don't need to add this part. You could immediately jump to stating what your a and b are. But I'm just going to write that for clarity, where a is equal to 5. And actually, let's stick with 1. A is equal to 1 and b is equal to 1. Or if you really want to be very concise, you can say a is equal to b, which is equal to 1, right? Since 1 is an odd integer, if you want, you can prove 1 is an odd integer by plugging 1 into our definition of an odd integer, where an odd integer is defined as any integer x, such that x is equal to 2k plus 1 for some k that has to be also an integer, and x is an integer. So you would say x is equal to 1, then you would say 1 is equal to 2k plus 1, and you have to rearrange for k, and if k does in fact equal an integer, then 1 is odd. But you've already seen me do that in previous videos, and I think I can just assume the reader, or you, the audience, knows this, so we can just immediately skip to our next step. We can then say, then a minus b is equal to 1 minus 1, which is equal to 0, and 0 is not odd. We can prove this by saying, here, proof let x be an integer such that x is equal to 2k plus 1, where k is also an integer. Suppose x is equal to 0, then 0 is equal to 2k plus 1. Then, or, so therefore, k must be equal to -1 over 2, and -1 over 2 is not an integer, so k is not an integer, so 0 by definition of odd is not odd. You can, of course, write this more explicitly, say x is equal to 2k plus 1, which by definition makes x an odd number, and then you can continue, and then you can just, after that, write what I wrote here. But now we can just write our conclusion. This makes the negation true, so the original statement is false. Awesome. So we've proven that the difference between two odd integers, any two odd integers, is not in fact odd.